When I started exploring audio programming, my deepest interest was in sound synthesis. I was curious, how is it possible that with a few lines of computer code you are able to make music? The very first technique that I learned was wavetable synthesis. It is a very basic technique, but it already allows you to generate a plethora of timbres and already to make your own electronic music. And in this video you are going to learn exactly how does wavetable synthesis algorithm work, and you'll be able to implement it yourself. Hi everyone, this is Jan Wilczek from the WolfSound.com, and in this video you are going to learn what is wavetable synthesis, how does it work, how to implement it. You'll listen to some examples of wavetable synthesis, you'll learn about pros and cons of wavetable synthesis, and ultimately you will learn how this technique relates to other synthesis methods. But first let's consider what in general is sound synthesis. Sound synthesis is the art of generating sound without using typical classical musical instruments. And from the analog days till today, we've come a long way in sound synthesis. And in this video we'll consider mostly computer-based sound synthesis, which means that we're generating sound using software. The sound generation process always starts with some user input, so a musician makes some kind of a gesture. And we could say that this gesture could be as simple as pressing a key on a MIDI controller keyboard. This input provides some what is called control data, and this control data is then used in our synthesis algorithm. And the synthesis algorithm does all the heavy processing and transforms this user input into a waveform, into a sound that we can listen to. In the early days of digital sound synthesis, the sound was generated using dedicated hardware, namely digital signal processors. Thus, there was a great need for methods that are both fast and memory inexpensive. Memory was quite expensive back then. And thus, wavetable synthesis was conceived because it is both quite fast and memory inexpensive. Although our computers are much more capable than the digital signal processor of the 1980s,
He's using a polymorphic engine to mutate the code. Whenever I try to gain access, it changes. It's like solving a Rubik's Cube that's fighting back.
these basic methods are still valid today and are quite useful to learn so that we can understand the broader scope of the sound synthesis landscape. Let's introduce the concept of wavetable synthesis by trying to design a sine generator. As we may know, a sine waveform is completely defined in terms of its frequency in hertz, its amplitude, and we'll assume that this amplitude is in the 0 to 1 range, and its initial phase, which for the need of this video can be neglected, so the initial phase will always be 0 for us. Having this formula, we are able to compute a value of a sine function at any point in time. As we know, on computers we don't process sound using the physical time in seconds, but rather we use digital samples. And samples are related to time by the so-called sampling rate, sampling frequency. This is a number that tells us how many samples, so how many discrete values do we produce per second. And we can compute the physical time using the time index and the sampling rate, and it is just the sample index n divided by the sampling rate fs, which gives us the time in seconds in our sound. When a user presses a key on a MIDI keyboard, we already get the information, the control data, which key was pressed, so we have the MIDI note number and how fast it was pressed, so we have the velocity of this keystroke, and out of this information we can already retrieve the frequency in hertz of the sound that we want to play and the amplitude. So we already could play our sine because we have a closed form formula for its discrete values. But how do computers and calculators calculate the values of a sine waveform? Well, normally there is not a dedicated function in hardware that computes a sine function. The computers use what is called a Taylor expansion. It is basically an infinite sum that contains the argument of a sine function raised to odd powers and divided also by rising constants. Of course, this sum is infinite, so our computers cannot calculate it precisely. So what they typically do is they truncate it at some point to obtain a fixed error, and this error could be even smaller than machine precision. But now let's imagine that this operation, which involves many terms and rising to quite high powers, should be performed 44,000 times per second. So if our sampling rate is 44.1 kilohertz, we actually would need to play a single sine to perform this sine calculation 44,000 times and 100 per second. And it's just for a single sine. And what if we wanted to play multiple sines at once? And that's exactly where wavetable synthesis comes to help. A wavetable is an array in memory which stores a fragment of a waveform. In case of a sine function, we could store one period of a sine in, let's say, 64 samples, and it would look like this. The values in a wavetable can be computed using Taylor expansion because we do it only once, typically before we start any processing of sound. The period of a sine waveform is exactly 2 pi. So if we store one period of a sine in a wavetable, we can compute the index that corresponds to a specific phase by using the ratio. So the ratio of the argument of sine, the phase, to the period of the sine, which is 2 pi, is equal to any index in the wavetable to the wavetable length, which we can denote by L. Okay, so with this ratio, we are able to get the index in the wavetable of our waveform for the phase argument, which is in the range 0 to 2 pi. But if our phase theta is outside of 0 to pi, we need to bring it back to that interval. So the sine function is periodic. Every 2 pi we get exactly the same value. So if we have our phase theta, which is outside of the 0 to pi range, we can simply bring it back to this range by subtracting the multiplicity of 2 pi that is contained in this theta, or if it's negative, by adding this multiplicity. And in software, it can be done using a function which is called fmod. It subtracts the multiplicity of 2 pi and leaves us the phi x argument, which must be in the 0 to 2 pi range. When we have our phi x, we can compute our wavetable index k by multiplying phi x by L and dividing by 2 pi, what is a result of the transformation of these ratios that we talked about before. Now, our k most probably won't be an integer, which means we won't hit exactly a value which is stored in the wavetable. So we need to somehow approximate that value using what we already know about the wavetable. And we have multiple options to use here. For example, we can truncate k to the nearest integer, which is smaller than k. This is also called zeroth order interpolation. We could also round k to the nearest integer. Finally, we could also use linear interpolation, which involves the weighted sum of the two values in the wavetable, which are nearest to the index k that we obtained. Let me show you that on a quick example. Let's say that here we have a fragment of our wavetable. So let's assume that our k was picked somewhere here. So this is our k. This is some, let's say, L, and this is some L plus 1. And this small L denote the indices that are in the wavetable. Okay, so we have our k. Now, if we wanted to use a zeroth order interpolation, then we truncate k, and we thus would go here to L, and we would pick exactly this sample value as the output for that specific K. If, on the other hand, we used rounding, in this example, the nearest integer to K is L plus 1. So we would go here, and we would output this value for that argument K. But if we used what is called linear interpolation, then we need to look at this straight line that goes from the samples corresponding to the indices nearest to K. So we look at this line, and then we find where this line crosses our K argument. And then we would exactly take this point, which is a weighted sum of the two nearest wavetable values, and nearest in the sense of wavetable indices. Each time we read out a value out of the wavetable, it is called a wavetable lookup. Okay, so the input from the musician gave us the amplitude and the frequency. And we know that for an arbitrary waveform, which we have period stored in a wavetable for, we can compute an arbitrary value over time. But we don't have to explicitly compute the phase argument for each sample that we want to produce. We can simply have some phase variable and increment it by some phase increment, let's say, which is dependent on the frequency that we want to play out and the current sampling rate. Whenever the frequency changes, we change this phase increment, and whenever a sound needs to be generated from the start, so for example after a key press, we can reset this phase variable to 0. How to compute this phase increment? Well, it's quite simple. We just need to subtract the phase at the nth output sample from the phase at the n plus 1 output sample, and that gives us 2 pi times f over fs. Alternatively, because we eventually will always do a lookup into the wavetable, instead of incrementing the phase, we may increment the index. So again, if a key is pressed, then we have an index variable which is set to 0, and for each successive sample we loop over the wavetable by incrementing the index by some value which is also dependent on the frequency and the sampling rate. And again, this index increment can be calculated as a difference between two successive indices for a specific frequency. And that gives us the frequency times L, so the wavetable length, divided by the sampling rate. As with the phase, the index needs to always be kept within the boundaries. So in the case of index, it's from 0 to L. And we can achieve it by either subtracting or adding L, depending on where our index currently is, or we can use the fmod operation, which was already explained. Now, which to use, like phase increment or index increment? From the implementation perspective, there is small advantage to using the index increment, because we then don't need to calculate from the phase to the index. But the phase argument has a physical meaning, so it's totally up to you which version you will stick to and implement. Now we can summarize our wavetable synthesis algorithm on a DSP diagram. We know that we get the amplitude and frequency information from the user. This can be calculated into the index increment on a sample-by-sample basis. So let me write k-inc, which is dependent on the sample index. It can change on a sample-by-sample basis. Okay, now we add it to the index from the previous iteration. And I write here z to the minus 1 because it denotes a delay by one sample. Now that we have our index, we can put it into the fmod L operation, which brings it back to the 0 to L range. Now, if we have our index in the 0 to L range, what we can do is two things. First, we close the loop by submitting the current index value for the next iteration. And second, we do a wavetable lookup. Okay, and with our wavetable lookup, we have a sample of our waveform. We now just need to multiply it by the amplitude. And this amplitude I also write as a sample dependent in case we want to use an amplitude envelope. And that gives us one sample of our desired waveform, which is the waveform that we have in our wavetable. By completing this diagram, we created a wavetable synthesizer. And this schematic shows what is called an oscillator. An oscillator is anything, let's say, that given an amplitude and a frequency and some reference like what waveform should it play, it gives us the samples. And wavetable synthesis is one way of realizing an oscillator. Oscillators are typically denoted as a semicircle or a semicircle with a rectangle. Oscillators are the workhorse of sound synthesis. As we will go deeper and deeper into other synthesis methods, you'll see how these oscillators can be combined and can interact with each other. Wavetable synthesis is just one way to realize an oscillator. Oscillators are sometimes denoted using the abbreviation VCO, which stands for voltage controlled oscillator. And this expression comes from the old analog days of sound synthesis, where electric voltage was used to control amplitude and frequency information, but somehow the name stuck. Okay, now that we know how wavetable synthesis works, we can implement it and listen to some sound examples. The first one is the sine tone generating using a wavetable with 64 samples at 440 Hz using 44.1 kHz sampling rate. Here's the result. As you can see, on the magnitude frequency spectrum, we get only one peak, which is great because that's the desired sign that we wanted to play out. Okay, now let's listen to a different waveform. Here we have a wavetable with a sawtooth, and the sawtooth is also 64 samples. And now we generate a sawtooth waveform using this wavetable. Here is the magnitude frequency spectrum, and it shows us what we already heard. There is some ringing. And here we discovered the major disadvantage of the wavetable synthesis. In principle, wavetable synthesis could be thought of as sampling a continuous waveform with some finite sampling rate. And the sawtooth waveform has an infinite frequency spectrum. And because of that, we sampled the sawtooth waveform with some finite sampling rate and thus introduced aliasing, which I discussed more broadly in a different video. And these aliased components can be seen as inharmonic partials in the spectrum of our output. Now let's listen to what happens if we play the same sawtooth waveform, but this time at the frequency of 880 Hz. That didn't sound very nice. And that's the problem with wavetable synthesis. The higher we go in pitch, the more artifacts we obtain. And for the highest notes on a piano keyboard, the sound does not even resemble the pitch that it was supposed to play. So for these harmonic rich waveforms, the only thing that we can do to prevent aliasing is to increase the sampling rate. But it's not always desired. Therefore, as it was a big problem in the early days of digital sound synthesis, and it was the primary reason why it was not an instant success in the 1980s, since then a lot of research was put into finding an algorithm that would generate a waveform which is not as harmonic rich in the upper frequency range, so it doesn't have any aliasing components. These algorithms that don't produce aliasing at high pitches are called anti-aliasing oscillators. And if you're interested in that topic, I've put some references in the description below, as well as in the full article over at wolfsound.com, and I highly encourage you to check it out. On the other hand, an advantage of the wavetable synthesis is that we can produce waveforms from arbitrary wavetables, and it will always be periodic and it most probably have the pitch that we want. So here I generated a wavetable using 5 different Gaussians. I subtracted their mean and also provided a fade in and fade out at the end, and here is how it sounds for 110 Hz. It sounds a little bit like a horn, doesn't it? Its spectrum is also quite interesting. And here's a field where wavetable synthesis provides a lot of space for experimenting. So how wavetable synthesis relates to other synthesis methods? Well, it is primarily used to have some oscillator implementations, and what this oscillator's output can be then used for subtractive synthesis, frequency modulation synthesis, amplitude modulation synthesis, and so on. Another very closely related technique is sampling. Sampling is a technique where you record real-world sounds, real-world instruments, and then you assign specific recordings to specific note numbers in the MIDI language. So in theory, you could play a guitar in a specific technique and record each note of a guitar with a microphone, and then assign each recording to a specific key on a piano keyboard, and then theoretically play the guitar using the piano. Actually, that's what I did on my music album The Fire Will Rise. Anyway, typically this recording to key assignment is not done one-to-one, because then we would need to store many recordings. So what is done is that only some notes are recorded and the others are interpolated using the recorded notes. But what is important is that for high pitches we have recordings, and recordings don't have aliasing in them. So that's the major advantage of sampling over wavetable synthesis. There are some more implementational issues with sampling, but I will not go into the details here. And wavetable synthesis could be seen as sampling, but with just a single recording and even truncated to one period of the underlying waveform. So the samples in sampling contain many periods, because the samples are even a second or up to 10 seconds long, and in wavetable synthesis we just have one period of a waveform. So if 1 second is 44,000 samples, then our wavetable is just 64 samples. On a closing note, I would like to mention that some variants of the wavetable synthesis exist. What we discussed was a single cycle wavetable synthesis, which means that we have only one wavetable and we loop over it constantly. In multi-cycle wavetable synthesis, we choose the wavetable that we play out on the go, and their order may be fixed or random. So for an example, we could concatenate the sine, the square, and the Sawtooth wavetables, and the result at 330 Hz would sound like this. But this is a little bit more complicated, because we effectively lengthen the period of our wavetable 3 times. So we lowered the played out pitch 3 times. So instead of hearing just 330 Hz, we hear more of a 110 Hz sound. So what is typically done, there are as many wavetables concatenated that the whole waveform is periodic, but the period, so the fundamental period, is below what the humans can possibly hear. So let's say below 10 Hz. But this is a more complex technique and I'll not go into details here. Finally, we have the multiple wavetable synthesis technique. And here we, at the same time, play out different wavetables. So we play out waveforms using different wavetables. And as a justifying example, we could think of it as when we press a key mildly, we only hear a sine-like sound. But if we press it fast and with a lot of strength, then the timbre, let's say, opens up and we get more harmonic rich waveforms such as the Sawtooth. And the impact of the specific wavetables on the output sound can change according to this user input. In summary, wavetable synthesis is an efficient method that allows us to generate an arbitrary waveform at an arbitrary frequency. Its low complexity comes at a cost of aliasing for high-pitched sounds. The advantages of wavetable synthesis are computational efficiency, the ability to generate arbitrary waveforms, and also the direct relation between the played out frequency and the parameters of the synthesis algorithm. Its disadvantages are the already mentioned aliasing at high pitches or even the moderate pitches, and also the necessity to introduce some further processing and or extensions to make the sound more musically interesting. Nowadays, software synthesizers typically use more sophisticated algorithms than just pure wavetable synthesis. Nevertheless, I believe that understanding wavetable synthesis is a great first step into the world of synthesizers. And if you understand the underlying principles very well, you will be able to implement many more synthesis algorithms, and you'll also better understand other synthesis algorithms. At the end, I have two closing notes. The first one is the complete tutorial on the wavetable synthesis is included in the link to article in the description down below over at thewolfsound.com, and I highly encourage you to check it out. The second thing is that during the development of the article and the video, I used multiple references. And if you want to learn more about sound synthesis, I highly encourage you to check them out. I've put the links to them in the description below, as well as in the article. In the next article, we'll implement a wavetable synthesizer in Python, and in the following video, we'll implement it in the Juice C++ framework. So if you like this type of content, then please subscribe to the channel and hit the thumbs up and turn on notifications so that I know that we're on the right track. And if you have any questions to the wavetable synthesis algorithm, don't hesitate to give them in the comments below. Thanks for watching and take care.